couple of announcements before the last regular talk today. It's sort of the last regular talk, but we do have this speed talk session. Maybe you noticed on the schedule, some number of students. Adele is taking care of it. 4 students, is that right? So they're 5-minute talks. We'll have a little break, a 5-10 minute break after this talk, and then start it. So it'll be maybe a half hour or something. So that's happening after this talk. So this is not the end of the day. And also to sign up for the for Deirdre's party if you're interested in going. There's a RSVP sheet on the front desk. Yeah, we'll definitely tell you the address, yeah, and the time and so on. I mean, yeah, you can walk. It's like a 20, I think it's 25 minute walk, right? I don't know. Yeah, I've done it before. It's not too far. It's Queen Street West. Yeah, so south and west of here. But we'll deal with that tomorrow. But today, make sure you sign up if you want to come, so she can plan. Okay, so we will. Our last speaker today, Tom Tucker from University of Rochester. Relations with rational functions, an alternative to the analog of the Tits alternative. Is that right? Yeah.
So I'd like to thank the organizers for putting this together. It's always fun to be back here. So I thought I'd start with kind of a really basic question that turns out to actually have a really nice answer. I'm just going to let f and g be 2 rational functions. Okay. Coefficients in C. The field that they're defined over does matter. Some of this really doesn't work in characteristic P at all. Some of it does. What I'm about to state next, I don't really need, but it's nice. The formula, it's nicer this way. Okay. The statement's a lot nicer this way. I'm going to take the degrees to be both greater than 1. It turns out if they're both 1, it's already subsumed by pre-existing theory. One of them's 1. You still get a very similar result. It's just not as nice, really. Okay. What relations, compositional relations, can f and g satisfy? So what do I mean by that? I mean, like, what kinds of non-equivalent words in F are equal to non-equivalent words in G? I think it's nice to do an example here. I'm going to let's say f of x equal x squared plus 1. Okay, and then I'll let g of x equal minus x squared plus 1. Okay. And it's pretty easy to see, right? When I start doing words in these in F and G, all that really matters is whether my leftmost thing is F or G, right? So you get stuff like, GF squared is the same thing, right, as G squared F, and so on, things like that. There's other ones too. Any compositional power, I'll get these things like that. All that really matters is whether your leftmost thing is a G or an F, because the G just shoves a minus in front, because they're both, right? Yeah, so basically, right, if I square G, don't forget, right, the minus goes away, but then it comes back in at the end, okay? So all that really matters for these words, right, is whether your leftmost thing is an F or a G, okay? So you might ask, are there other types of relations that these functions could satisfy? The answer is no, not really. Sort of, but not really, okay? So what do I mean by sort of, but not really? So here's the theorem that we can prove, okay? I'm going to do one slightly funny notational thing you might not be used to, right? So these aren't 1-1, right? So they don't generate a group, they generate a semi-group, okay? So when I write something like this, I mean the semi-group generated, okay? I mean, usually this means group, but we don't really have any group that these guys fit into, right? So it's just a semi-group. Okay, so here's the theorem that we can prove let me give myself a tiny bit more room to state it over here. Okay. So I'll state the whole thing. And so I'll just let f and g be two polynomials. Okay. Sorry, not polynomials, rational functions. I'm going to make the degrees be greater than 1. You still get good stuff if they're not greater than 1. It's just more complicated and somewhat subsumed by earlier stuff anyway. Okay. Then there's two possibilities. Okay. One of them is that they don't satisfy any relations at all. The semigroup on f and g is free. Okay. So when I say free, what do I guess I really mean is free, i.e. is the free group, free semigroup on two generators. I guess you say on two generators. Okay. So that means, right, take any word in f and g, take any two words, if they're equal to each other, it's because they're just the same word. Okay. Or you can see these pretty easy to see that these are mutually exclusive, right? Or the other possibility is that's basically abelian. They almost commute. Now, I'm using this terminology. I'm just going to put it in quotes. I'll tell you exactly what I mean in a second. Okay. So what do I mean by almost commute? What I mean is if I take the group they generate, it's very, very close to being abelian. Okay. Now, unfortunately, we're dealing with semigroups here, so concepts like kernels and indices and stuff become completely terrifying. Okay. So we're not going to use any of those things, but there is a nice thing we can say here, which is this. There's two ways of saying it. Okay, one is that you can say this. So there's a constant b, okay, depending on f and g. It depends definitely on f and g, such that if I look in this semigroup, okay, and I take all the things okay, that are in the semigroup that have a fixed degree, okay? Just fix a d, that any d you want. Take all the things of fixed degree, okay? The size of these is bounded by d. Okay? So as I move along, right, I mean, let's just say f and g, let's just suppose they have the same degree, okay? I take words, right? The word length determines my degree, right? If I take the word length, I only get at most b different words, say, of that length. The set of all theta that are in the semigroup that have degree d for some fixed d, okay, is less than or equal to b. Sorry, say that again.
I think that this is fixed d.
So, sorry, show me where. Sorry.
The description just to the left of the right front.
The direction. Oh, number.
No.
Oh, such that. Sorry. There. Sorry. Such that. Sorry.
So B depends on D.
B depends not on D. That's the whole point. B is independent of D. The B does not depend on the degree. No matter what the degree is, the same. So the B depends on F and G, does not depend on D. So fix any D. No matter what D is, this works with the same B. Let me just say this, such that for any D, let me write it like this. Let me quantify it a little better. Okay. Such that for all D, I'll quantify over D, such that for all D, the set of this is less than, the size of this is less than or equal to B. So no matter what, so it's that, let me say this, the B is independent of D. It depends on F and G, obviously. Well, I shouldn't say obviously. I'm not even sure if you could maybe bound it in some, well, yeah, I'll just say, you could make the, by picking your F and G the right way, you could make B as large as you want, but the D doesn't, it does not depend on the degree. What's that? Yeah, degree is a rational function, yeah. Such that? Sorry, say that again?
Oh, if the camera is not switching to the right board,
Oh, I'm sorry.
it's not your fault.
Oh. Yeah, so almost commute means, right? So what this means is that you go up, there's not that many different, if I take all the words of the same length, okay? So let's just suppose that it's easier to visualize this when they have the same degree. When they have the same degree F and G, right? I just take all the words of a certain length. There's only a bound on the number of words of that length that doesn't depend on the length. Okay. Let's go back and look at this example here. So this is sort of the master example. For this, there's only two. Okay. The number of things in here of a given D is at most two. Not, I mean, for odd things, there'll be none, right? But for things of degree 2, 4, 8, and so on, there'll be exactly two words, right? It'll be, the two words will be two distinct words, right? I can either be this, I can either be minus F to the N, which is GF to the N minus 1, or I could be F to the N. And that's it. So I only get two, so I only actually get two different rational functions here, okay, of any given degree, okay? So it would be great if we could phrase this in terms of like an abelian semigroup of finite index or something like that, but it doesn't, the index doesn't work great for semigroups, okay? The way I like to think of it is this, actually. I like to think of it like this, okay? I have a degree map, right? It just sends everything in here. What does it send it to? It sends it to the natural numbers, okay, right? And when I look at this, right, so this is the degree restricted to that. So there's this sum B, right? Such that degree inverse of N is bounded independently. Let me call it D, okay? Is bounded independently of D. Okay. So it's really just like you have this map to the natural numbers, right? With at most B things going to any natural number, right? It's a group it's a semigroup homomorph, and it's a semigroup homomorphism, right? Again, you'd like to say like finite kernel, but things like that don't really make a lot of sense for semigroups. Okay, yeah.
Really quick, is this necessarily equivalent to saying that we have finitely many propositions with a given number of F's and G's in them? Because if F and G are the same degree, it's the same, but if they differ, it gets a little more.
Yeah, if they have different degrees, so it actually turns out, by the way, that they don't. So yeah, so it's a little bit more. So that nice way I said it, when they have the same degree, doesn't work quite right if they don't have the same degree. Yeah. So if they have the same degree, it's sort of like, I mean, it's sort of like their image in here is cyclic, kind of, you know. And if they have different degrees, then I mean, if one degree doesn't divide the other, what you'll get in N won't be cyclic. Okay. Now it actually turns out that you can actually, they will actually live in some cyclic thing in N if they're non-exceptional. It turns out. Okay. But if here's an example where you have different degrees. They're not interesting examples, x squared and x cubed, right? Those are the only kinds of examples where you don't actually, where their image isn't actually cyclic, it turns out. Where this is true, but their image is not cyclic. The only way that can happen, it turns out, is for the exceptional ones, Chebyshev, powering maps, and Lattès maps. Yeah, so let me say what it doesn't say, okay? Then I'll say a little bit more about what it does say. So, like, here's a question. You might ask, is something like this going on? And in all the explicit examples, it is what's going on, actually. You could think, well, maybe something like this is happening. Again, I like to restrict to same degree. It's in no way, shape, form important, but it's a little bit more, as things become a little bit more intuitive. You might ask, well, actually, maybe I won't use same degree on this point. Is it just something like this, right? So that's what happened with my x, minus x squared plus 1, right, was just, minus 1 minus x, maybe I'll call it, right, composed with x squared plus 1, right? So you might ask, is that where it comes from? Must I have this? Must I have this? That would be in case 2.
Where sigma is.
Some sigma, some change of variables. Having some sort of skewy commutativity relation with them, like how minus 1 doesn't commute with this, but it sort of skew commutes with it. Is something like that going on? Is it like this, where you just have a couple automorphisms and you move along and all the stuff of the same degree are just related by this automorphism? No, actually, not necessarily. That's not obvious. For polynomials, that is what happens, but HexCE has some nice examples. Not very explicit, but very nice. Showed no. Okay, so it's not the really, really simple thing that you think is happening, but it's the next most simple thing, right? You're not just getting, again, I like to restrict it. There's no complication of any kind with letting the degrees be different, but it's easier to think of it sometimes with the degrees being the same. Think of the degrees being the same, what you might think, okay, well, the reason that I'm getting this bound is because the same length words, they're just some little finite list of automorphisms that connects them, that moves them around. And that's not necessarily what's happening, but it's the next most simple thing, okay? There's not an obvious relation between them, the ones of the same degree, but there is a bounded number independently of the degree, okay? So I'm actually going to say a tiny bit more about number 2. I'm mostly going to focus on number 1, okay? So the dichotomy is this. There's 2 possibilities here. Either the preperiodic loci are the same or they're not. Okay? So if they have the same exact preperiodic locus, okay, then we're in case 2. I'm not going to say very much about this proof, okay? Except this. So it turns out that if the preperiodic loci are the same, then by work of Baker and DeMarco, how does the proof go? Because then you have that the measures of maximal entropy are the same, okay? This is by Baker DeMarco. Higher dimension, it's Yuan Zhang. And then there's like a huge body of work on the kinds of relations you have to satisfy if you have the same if you have the same measure of maximal entropy. There's Schmidt-Steinmetz results. There's Bearden results for polynomials. So really, really nice summary in Hesch's paper. All kinds of interesting relations. Okay, between F and G. Okay, you can piece them together to get 2. Okay. What I want to talk more about is case 1, when the preperiodic loci are not the same. Okay. Oh, I should say who this is due to. This theorem is due to Beaumont, a student of Serge Contaz, and of Keping Huang. Oh, sorry, Jason Bell. Trying to actually do them in alphabetical order. Keping Huang, Wayne Pang, and me. Okay. And I'll say a little bit about what we did and what Beaumont did. Okay. So the case part 2, if the prep F equals prep G, that's in the earlier paper of me and Jason and Wayne and Kepping. Getting this is in a preprint of Beaumont's that came out maybe about 6 weeks ago. Okay. So I'll state Beaumont's theorem. So Beaumont's theorem is that if the pre-periodic loci are not the same, then it's free. So by the way, just for the rest of the talk, until the very, very last question I ask at the very, very end, f and g will always be rational functions of degree greater than 2 over C. So if I say f and g, that's what I'll mean. Hold on one sec now. I'm going to do something a little bit different here. I'm going to take, so if I call them f and g, that's what they'll mean. So I want to give them a different name, okay? So all of this stuff, I should say, everything in case 2 depends a lot on being over C. It's essentially all false in higher dimensions, all false in characteristic P. In characteristic P, it's especially false, okay? For example, if I take any 2 just polynomials over FP, any rational functions over, just defined literally over FP, isotrivial, they will have, right, the same, all FP bar will be pre-periodic, right? So they'll have the same pre-periodic locus. But if I pick 2 random rational functions, well, what are they going to do? They're probably going to generate a free group, okay? So I would say part 2, right, where we derive it from the pre-periodic loci being the same, in characteristic P, it's as false as it could possibly be, okay? So here's the theorem of Beaumont. So I want to be really clear about this here. I'm going to just state it Pn to Pn. It's actually true for polarizable maps as well. This is at totally the other end of the spectrum. Not only is it true, okay, in any dimension, it's also true over any field, any finitely any field at all, okay? Okay. And both degree greater than 1. Okay. Then, if they don't have the same pre-periodic locus, they don't satisfy any relations of any kind. Okay. The semigroup that they generate is free. I'll just say is free when I have 2 different things. When I mean that they that what they generate is a free semigroup on 2 generators. Okay. So this is true any field, any characteristic. Nothing really comes into it at all about the field. Before I do this, I might tell you how do you prove semigroups are free in general, or groups for that matter. Bain tool is something usually, there's probably somewhere else where something is used, but very often it's something called the ping pong lemma. And the ping pong lemma is extremely easy to state. So how do we prove this? It's the ping pong lemma. Okay. I will prove it using the ping pong lemma. Okay, so I want to state this, I want to draw a picture and I want to state it slightly carefully. So what's a little bit, so the ping pong lemma is something that appears in, all over the place for showing that groups are free. The one twist here is that the proofs I'm familiar with where it's showing that a group is free group is acting on some space, okay? And the ping pong lemma is just operating on subsets of that space, okay? The novel thing here, I don't know if it's that novel really, is that I'm not gonna do this, okay, with how theta 1 and theta 2 act on Pn. I'm gonna derive other maps from them acting on a totally different space. I mean, not totally different, but pretty different space of functions, and apply the ping pong lemma there. Okay, so here is, it's really nice pictures with the ping pong lemma. Okay, I have two sets, okay, U1 here, okay, and U2 here. I'm doing a particularly simple form of it, okay, where the whole space that they're acting on is just U1 union U2. Okay, so I've got two maps from U1 union U2 to U1 union U2, okay, and here's what happens, okay. So what happens is alpha 1 just sends everything into U2, okay? And maybe I'll do it the other way around. Alpha 2 sends everything from U1 into U2. Alpha 1 sends everything right back, okay? And I'm also going to put in one more thing. I want these to be injective. Okay, I want these to be injective. And then alpha 1, alpha 2 is free. Oh, sorry. So I should say that too. Alpha 2 sends U2 to itself. And yeah, let me put a little circle in here too, and a little circle in here too. So alpha 1 sends U1 to itself and sends U2 to U1. U2 sends U1 to itself and descends into that. So what you might visualize here, because this is exactly what it will be, in fact, is that these are very strong, like contracting maps of some kind. So maybe the center of U1 is some kind of a fixed point for alpha 1, and everything gets sucked into it, okay? And it's very strongly attracting, right? Because it's just taking literally everything, just going in there. And once I'm in there, I'll just get closer, okay? So why is this free? It's quite easy to see. Alpha 1, alpha 2 are injective, so I can cancel them from the left-hand side, right? So here's a really simple way to do it. No matter what, right? No matter what words I pick, these can never be equal to each other, right? Because I take whatever I start with. If I end with alpha 1, right, I'll end up here. No matter, I could start with that same thing. If I end with alpha 2, I'll end up here. Therefore, the words can't be the same, okay? And then since it's in, you do need a tiny bit more, right? Because these are semi-groups, not groups. I need these to be injective so I can then just cancel. Cancel, 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 cancel. I start with a word, right? I can cancel the first two things. They've got to be the same. I can cancel the next two. They've got to be the same. Well, and behold, what am I left with at the end? Nothing. Okay. Okay, so the whole trick here, really, in a way, Beaumont has a very, very clever way of finishing this off. But in a way, the whole way to set this up is to figure out what kind of space, okay? I have these maps, P1 to P1. I can't do this at all with my maps. Maybe you can. I have no idea how you would. What I want to do is create some other map associated to them, acting on some other space, okay? Or I can apply the ping pong lemma, okay? And what is that space going to be? It's going to be a space of height functions, okay? So let me state this part carefully. There's quite a lot that goes into this, but it's not super hard in a way. I mean, it is, all the theorems leading into it are hard, but it's, so I'm going to state this as a theorem, okay? Now, there's quite a lot of people I maybe would put on this. You've got Tate, I guess. You've got Call, Silverman. Probably I should include Northcott in here as well. Okay. And then finally, Moriwaki. Okay. So one thing here, you might say, notice I said over any field that I want. Right now, it turns out, of course, theta 1 and theta 2, they only have finitely many coordinates. So I can assume they're in a finitely generated field K. Right? So let's let K be a finitely generated field. Okay. And I'm going to work over Pn here. Okay. There's a function. It's a height function. Now, by the way, I don't use a whole, in this proof, we don't really use a whole lot about it being a height function. In fact, there's actually situations where you can do stuff like this with functions that aren't really height functions. Like, for example, you can do this with local height functions very often, say, for polynomials. So I'm just going to say a function. Okay, I don't really care that it's a height function. Okay, it is a height function, but it's not super duper important. Okay, and I sometimes wonder, right? So I'll go through this to R. So it's got some function. Okay. Yeah, so I'll state this out, and then I'll try to say something about, like, do I really, is there some other thing I could use that's not a height function? I don't know the answer. So I've got a height, there's a function h, okay, such that for any map, for any theta, okay, from Pn to Pn, okay, defined over K. Okay. So I'm going to let theta, I'm going to let something called alpha theta, okay? Alpha theta is going to sort of be like theta star, but I'm going to normalize it by the degree. Okay, so I'm going to create a map. Okay. The map, I'm going to call it, alpha, alpha theta. So what is alpha theta going to do? Okay, alpha theta, okay, it's going to take any map, is going to map this thing to itself, what I'm going to call capital H to capital H, okay, where H is what? H will just be the set of all functions, okay, P and K bar to R, that have that are bounded in difference from H. Okay, so it'll be the set of all maps. Maybe call it capital G or something like this. Capital G. Okay, from P and K bar. So I'm not really putting much of a restriction on these at all, such that the difference between G and H is bounded. Okay, subnorm. Okay. Given by, what is alpha theta going to do? This might look pretty familiar to you if you haven't seen it before. It's a little bit like it's the tape procedure. Okay, I take my of G. Sorry, if I take alpha theta of G. Okay, what is it? It's just the function that I get if I divide. Okay, by the degree theta. By the way, I do want to, I always mean to have the degree here be greater than 1, or none of this works at all. I take 1 over degree theta, and then I take, maybe I'll call this theta upper star G. Okay? In other words, 1 over degree G, 1 over degree theta, times G after theta. Okay? So I just pull it back, and I divide out. And this map here is a contraction. Okay, with contraction multiple (1 over the degree). theta. Okay, so what does that mean? Let me say this really carefully. If I take a G1 and a G2, and I hit them both with alpha theta, right, they get closer to each other, okay, by at least 1/degree theta, okay? If I do this out, what I end up with is that alpha theta of G1, okay, minus alpha theta of G2, okay, is less than or equal to, it's actually exactly equal to, but all we need is less than or equal to 1, okay, over degree theta, okay, times what their initial distance was, okay. There's nothing fancy, just a usual contraction map. It's very crucial that the multiplier be 1/degree theta, though. So I get this contraction map, and furthermore, right, the fixed point which I'll call h theta, okay, of alpha theta has this property. And this is really where the heavy duty stuff comes in. H theta vanishes exactly on the pre-periodic locus of theta and nowhere else. So H theta of Z equals 0 if and only if a Z is in the pre-periodic locus of theta. Okay. So that's our setup. We originally stated this, me and Jason and Kepping and Wayne, in a slightly more clumsy way, I'd say, where we're kind of explicitly doing tape telescoping series. Beaumont sort of refined it to this sort of more elegant way of looking at it. Okay. So what I might start by saying is this. At this point, what Jason and Wayne and Kepping and I did was pretty simple. We did this, and it's really quite easy to see how this will go. This is the Bell, Wang, Peng, me thing. Okay. If I take that same setup, if these are both maps Pn to Pn, okay, not equal to prep theta 2, then, so this is really an easy application of the ping pong lemma. Then there is an L. It's really all sufficiently large L such that, so for this I don't actually get, okay, that theta 1, theta 2 is free, but if I put them up to a high enough power, they become free. Okay, now this is actually extremely easy using contraction maps. Why is that? I just draw a little circle, okay, around the canonical height for theta 1. This is in that nice big space H, okay. Draw another circle, okay, around H theta 2, okay. And it's a contracting map, right? So eventually everything in here is at some bounded distance from this, right? They eventually just get sucked in. I might have to iterate a bunch of times though, before they end up in here, right? When I could start here, hit it with alpha 1, hit it with alpha theta 1. It might take me a while to get closer, but I know I eventually end up in there, right? Because everything in here is at a bounded distance from here, and that distance just gets sucked in. The distance recedes, and I eventually end up in this little circle. Okay, so in other words, what's my setup here? So my setup is alpha theta 1 sends everything into here, and alpha theta 2 sends everything into there. Okay, therefore, by the ping pong lemma, it's free. We're done. Ping pong. Okay, so that's quite easy. Now, there's something you might notice about this, okay, which is I didn't really need anything at all about the multipliers for alpha theta 1 and alpha theta 2 at all here, right? No matter what they are, the distances are going down by a certain amount, I'll eventually end up in here. If I start in here, right, I'll eventually end up in there, and after a bounded number of steps, because the distance is just going down by this multiplier every time. So it doesn't matter what the multiplier is, as long as it's less than 1 for this, okay? So the first thing you might ask yourself, for Beaumont's theorem, right? For Beaumont's theorem, I don't have an L in there at all, okay? You might ask yourself, in Beaumont's theorem, well, is it true if I just have 2 contraction maps, okay? They've got to have different fixed points, okay? Let's say they're injective. They've got different fixed points, okay? Is it necessarily true that the semigroup that they generate is free, right? And the answer to that is no. What ends up happening is that the multipliers work out sort of miraculously perfectly to make the theorem work. So let me go through this. Yeah. Yeah, it probably is exactly the height. Well, I don't know if it's exactly the height pairing. It's definitely related. Yeah. So it's the Zhang. I'm sure that let me think about that for 1 sec. Height pairing becomes trickier and higher dimensions. There's something or another you could bound it with, though. Yeah, I think you'd have to take right. So I'm now on a higher dimensional thing, so I can't just pair the 2 line bundles, okay? But I could do various combinations of the line bundles, I think, and get, I'm sure I could bound it in terms of some kind of intersection between powers of the 2 line bundles, yeah. In dimension 1, right, I think in dimension 1, by the Zhang essential minima, I think the distance is, I forget what is it, like twice or half or something like that. Right, it'll be, the distance would be bounded. I would be bounded above by the height pairing, I guess, yeah. In higher dimensions, there's something you can bound it by for sure. Okay. Well, it doesn't really matter in a way. I know that they're bounded distance. I don't care what the distance is. Eventually everything down here will end up in here and everything down there if I iterate enough. Okay. So Beaumont's improvement is getting rid of the L, okay, and making it a 1. Okay. And there the multiplier is crucial. So let me just start with this. Okay. So now let's forget all about all the rational function stuff and talk about something a little bit more elementary, which is contraction maps on complete metric spaces. Okay. So here's a question. Yeah, I'm just going to call these alpha 1 and alpha 2. Okay, let alpha 1, alpha 2. I'm not going to call it maybe H anymore because I don't want to make it sound like it has anything to do. It's really any complete metric space. Okay. I do want it to be complete, so I actually get my fixed point in there. Okay. With distinct fixed points. Okay. And I'm going to give them each a multiplier. I'll call one multiplier C1, one multiplier C2. Right, so the multiplier is just how much it knocks the distance down by. It could knock it down by more. That would be okay too. Turns out it doesn't for ours. I think actually, hold on 1 sec. Let's actually make this be exact. Do I need it? Well, I don't think I do. Maybe I won't have it be exact. C1, C2. Okay, multipliers. Contraction, multiples, whatever you want to call them, okay? Is alpha 1, alpha 2 free? Necessarily. Let's have them both be injective, too. So they're injective. I'll draw a little bit of a picture here for a sec. The answer is it doesn't have to be, no. Let me again draw this picture here. So what do I mean? I've got a fixed point, right? For alpha 1, maybe I'll call that P1. That's my fixed point for alpha 1. There's my alpha 2. Okay. So I do know by this exact same argument, if I throw up enough powers on them, it will become free. Okay. But that doesn't mean it's free at the first power. Okay. So the answer is not necessarily. Okay, what's an example? Okay, So the example I'm going to use, I'm going to take beta. Okay, I'm going to take a beta that solves 1 plus beta equals beta squared. Okay, beta will be a number between 1/2 and 1. And I'm going to take alpha 1 of x will just multiply by beta. Okay, and alpha 2 of x, okay, will multiply by beta and add 1. This is not free. Okay. This isn't too hard to work out. What ends up happening here is that alpha 1, alpha 2 squared is the same thing as alpha 2, alpha 1 squared. Just totally elementary. Okay. Now that had to do with my specific choice of beta. So I can actually do this particular thing only works nicely for beta solutions of this. The beta solutions of this will live in 1/2, 1. So now I'll state Beaumont's theorem, and I can actually say a little bit about how he proves it even very quickly. Okay. It has to do with the multipliers. Okay. The proof is really, really nice. It's almost sort of the matter of finding what the right conditions are in a way, more so than it is actually proving it. So I'm going to let alpha 1, alpha 2 be 2 contraction maps. Injective. This will be a complete metric space. Okay. Injective. Different fixed points. And now I'm going to put my condition on. So they have to have different fixed points. It's totally false if they have the same fixed point. Now I'm going to put a condition on the multipliers, okay, that miraculously makes it work perfectly for rational functions. Okay, with multipliers, C1, C2. And I'm going to put a condition on C1, C2. C1 plus C2 less than or equal to 1. Okay. Then alpha 1, alpha 2 is free. Okay. And let's notice, right, that if I do this for rational functions, C1 is 1 over something bigger than 1 is an integer, and same for C2. So it's enough. As soon as you take so this example, you can make the beta smaller and smaller and smaller by doing 1 plus beta squared and so on. Okay. So as soon as C1 and C2 is bigger than 1, it's false in general. If I pick random contraction maps, it's probably still true. So the proof's actually really simple. What's that? No, they're both positive, right? I mean, they're both things relating distances, so they're both non-negative, right? So like what I mean is that the way this works, right, is that alpha I x1, right, minus alpha I x2 is bounded, right, by C2, bounded by CI. Yeah. So it's just your contraction multiple. So it's just how much it's shrinking your distances, okay? And actually, by the way, for ours, it's not a less than or equal to, it's actually equal to, but the proof doesn't make it equal. Okay, so a proof doesn't require it being equal proof. So it turns out there's sort of 2 cases, okay? So what you do is this, okay? I let W equal all limit points okay, of sequences going like this. Alpha I1, alpha IN. I fix some point P. So I fix a P. Doesn't matter which P, as long as it's not a fixed point. And I just start running this on it. I just start taking longer and longer words, okay, in my alpha I. All these things are Cauchy sequences. If I take a sequence of zeros and ones, it gives me a Cauchy sequence. And this W will be compact. Okay. Turns out not hard to prove that it's compact, not hard to prove these are Cauchy sequences. Now there's now here's the really, really beautiful thing. It satisfies this beautiful self-similarity relation, right? Because what happens, right? I just throw on a new sequence element and I get that. So I have this self-similarity thing. Then there's two cases, okay? One, this seems like it should be the easier case. It's actually the harder case. Turns out that if C1 plus C2 is less than 1, this self-similarity relation forces W to be totally disconnected. It doesn't matter at all that it's totally disconnected, although it is. W is disconnected. Now, it would be an exaggeration to say that what you do is then ping pong between two components of it, but that's the idea, okay? Not exactly what you do. Okay, the second possibility, which is actually turns out to be much easier, is that it's actually equal to 1. Okay, when it's actually equal to 1, you end up with a Hausdorff measure. You end up with a one-dimensional Hausdorff measure, and you do a one-dimensional Hausdorff measure. Ping pong lemma. What you do is show that you can show then that the alpha 1 of W and alpha 2 of W, their Hausdorff measure is 0, okay? If I had two words that were equal to each other and I hit W with that, I'd end up with something that Hausdorff measure was not 0. So this ends up, this part is really like the ping pong lemma, really basically exactly, almost. This part here is, you have to tweak it's not exact. I always want to say, well, now you're just going to ping pong back and forth between two components. Not exactly that, but it's similar to that. So amazingly enough, what you get is this, right? This condition here is automatically met by all the contraction maps coming from rational function, coming from maps Pn to Pn, and it finishes your. I'll maybe close with one quick question. This will just take maybe 30 seconds to write. What about characteristic P? There, I have no idea what happens. Okay, let's just let these be two rational functions. Fp of t, degree f, degree g greater than 0. Sorry, greater than 1. Can you say anything at all anything smart? Let me say this more intelligently. So they're let me say of x, t looks like I'm adding an indeterminate. So they're trivial polynomials in the they're trivial rational functions in the variable x. So they're just fp polynomial over fp polynomial, or q, doesn't matter. You know, maybe even fp bar, doesn't matter, about fg at all. Okay, and I have no idea. So everything completely falls apart in characteristic P. The reason is these guys will have the same periodic points automatically, but odds are it's free. So it fails really utterly and completely just for trivial rational functions. It's really not clear at all what's true. No, yeah. So we don't. So we've done. I've done a lot of examples. So the most natural examples to try are just polynomials. Now, if the degrees of the polynomials are prime to the characteristic, you actually can use Botcher coordinates. Everything's quite easy, even much easier really than the stuff I did earlier. If they're polynomials and their degree is divisible by p, the one natural thing to try is Drinfeld modules, right? And even Drinfeld polynomials, we can't really do anything. I mean, I will say this, all the examples that we try, they are either free or almost abelian. But it's just, how do we do that? We just like grind through with, computer algebra and we start to see patterns and then we conclude. There's nothing even remotely resembling the proof.
Any questions?